This conference will now be recorded.
All right, today's speaker is Tawfiq, and he'll take it away from here. Thanks.
All right, very good. Let me share. I'll do the presenter view. So can you see very well?
Yes.
Can you see?
Yes,
Oh,
yes, we
very
can.
good. Thank you. So this is a presentation from the ISCA workshop that DJ and company, did last summer. It's a reiteration of that. I'm also doing a keynote at EPEPS actually in next month, and I will share some of that content as well. It'll be expanded view of that. So I want to talk to you a little bit about data center power efficiency. And that's for me and my colleague, Anshuman Mittal at AMD. I want to recognize also people like Radha Swaminathan. I borrowed a few of his slides, like you can see, and some other folks as well, like you can see here at AMD. Okay, I'll give you about 20 minutes to read this legal statement, ask any question. I'm just kidding. I have to flash that one. So let's move then to the outline. So first, folks, I'll go over some fundamentals and trends of power and performance. I think that would not surprise anybody. A lot of it is actually a collection from things that already published on the internet and you probably have seen in various conferences. Then I want to talk about data center power and performance trends. And then we come, the topic dear to everyone's heart here is chiplet technology, which I think many people view it as an extension of Moore's law, and I can show you basically why. Then I'll talk about something more specific, which is power and power delivery and power management opportunities with the chiplet technology, how it would enable that. And finally, summary. Yeah, please feel free, to interrupt and ask any questions. Okay, so what is Moore's law specifically? I think we all hear about Moore's law slowing down, and that's very, very true. But why is that happening, and what's Moore's law? So let's talk about the basic fundamentals, right? Which is, hey, basically with every new generation of technology, Moore's law, if you like, predicted, hey, we're going to shrink the dimensions, the linear dimension by 0.7x. You just take that transistor, and in every dimension, you make it smaller by 0.7x. Now, if the linear dimension is scaled by 0.7, then the area scaled by half, right? 0.7 times 0.7. You could think of it this way, or more commonly known as Moore's law, the number of transistor doubles, right? For the same unit area with every generation. Now, when the vertical dimension here, across the metal oxide, also shrink by 0.7, the electric field, which is basically voltage over that dimension, that linear dimension, shrinks by 0.7. But you can't keep increasing the electric field indefinitely because that will break the dielectric, right? So what happens then, you scale voltage also by 0.7. So the linear dimension scale by 0.7, voltage also have to scale by 0.7. You look at capacitance, which is simply A over D. You look at that, it's also scaled by 0.7. Now delay, scale also by 0.7. You have shorter interconnect, faster transistors, which translate roughly, that's 1 over F. So frequency, improve roughly by 40%. You look at power, CV squared F, right? So that's scaled by half. So now you take all these scaling, and you get this beautiful Moore's law thing that says the number of transistor doubles, the frequency improves by 40%, and the power is reduced by half with every generation. And that continued to be true for decades, right? And nobody exploited that, obviously better than Intel, right? Until, of course, you start going into, against physics. Those, as you keep scaling this oxide, It's only few atomic dimensions now. And when it's so, so small, you have all these effects such as leakage going like crazy, power no longer scaling by half. To the contrary, leakage become very important portion of the total power and is increasing, exponentially, actually. So the situation scales a lot when you start getting into this sub-nanometer, the few nanometer kind of gates. And you see that manifested at the product level with the curve like this, which is I'm borrowing from my colleagues Dale Becker and Canon Goes. But you can see why the frequency started saturating. And this is for the single thread performance. The transistor count continues its exponential, right? But the frequency, you can see the power also starting saturating. You can't cool those devices. You can't deliver the power. So that's what has been, known as Moore's law, slowing down because of these reasons. Okay, so as I said, you probably all know all of that stuff. Now let's talk about data center power trends. Now let's talk about performance before I talk about power. So Moore's law, which says, every generation, roughly every 2 years, we're going to increase performance by 40%, and we're going to double the transistor. If you look at some of those workload in the data center, that performance is increasing significantly, actually faster than Moore's law, right? And that actually led to applications, enormous, very good applications, like you see here, like climate change modeling, space exploration, new drugs, machine learning, all of those applications powered by this incredible, performance, exponential performance increase that seems to be, continuing and is, and fueling all this, data centers. So the question is, what's going to happen to the power, right? So if we look here, and by the way, the predictions about performance tend to be very, very accurate. It's exponential, and like you see here, it's actually predicted very, very well. So because of that, by the way, performance increase. 10 years ago, there was a commission by Congress about data center power. There was a big scare that it's going to actually, there's not going to be enough power to fuel data centers, right? And surprisingly, by the way, and they predicted, hey, data center power will increase at least 10% every year. But over the last 10 years, data center power increased only by 6%. And I explain why, right? But the performance turned out to be correct. We continue on that performance trend. But power did not do that. So we're going to talk about that a little bit more. So what was happening on the power side, okay? So, by the way, just to give you some tidbit, so today, depend which model you believe, but I think it's, most of this actually number I'm showing here, you could think of it as 80% measured and 20% model, because not everybody reports, but a lot of the big cloud providers do report their energy consumption. So today, it's about 200 terawatt hour consumed by data center worldwide. There's about 1 billion core in use. That statistics, we heard all at OCP last November by Zane Ball and company from Intel. Let's talk about PUE. PUE basically is the power. It's a metric. It's the power entering the data center over the power used actually by the server. In other words, by the server boards used by the electronic equipment basically doing the work. The reason there's other things like building, air conditioning, cooling, fan, all of that stuff. And if you look about a little bit over a decade ago, that number was on the average over 2.5. So only less than a third of the power is actually used by the IT equipment. The rest, if you like, is wasted on the infrastructure. And if you look at that number, has been improving very dramatically. And today the average is about 1.67. So already, that's a 50% reduction in power waste, if you like, in that data center. But more importantly, if you look at the best in class reported by Google, is about 1.1, which means, just roughly 10% only. What used to be 2/3 of the power is now less than 10% used by the, wasted, if you like, in the infrastructure. It also tells you there's a lot of room to improve. If somebody was able to get to 1.1 and the average is 1.6, well, there's enormous amount of power that can still be saved if everybody can shoot to 1.1. And that very nice paper on how they achieved that. Maybe we can talk a little bit about it. Google is the first to compute the term to come up with the term compute energy proportionality back, I think, in 2007 by Andre Luiz. He's currently a fellow at Google. But basically the concept here is you only want to spend energy on compute and the minimum energy you need to perform a task. So your energy is proportional basically to your compute. And if you look at data center today, I'd say we're still far. We're still quite far from that, as I'll show you. And I think this is where we talk about maybe the chiplet technology, helping. Another fact, peak power is the number limiter to performance in data center. Okay, because the average power is actually quite less than the peak power. But there are those very small moments, sometimes in seconds, maybe a minute or something, where the power is very, very high, but you got to build the hardware for that peak power. So managing that peak power is very, very key, to reducing hardware, if you like, and for sustainability, of data centers. We'll talk about that as well. Now let's talk about trends. Now in 2025, 2030, again, I quote this from OCP last year, November 2021. People are expecting, okay, today it's 1 to 2% of the worldwide electricity used in data center. They're predicting like 20% of total electricity, okay, by 2030. People like Zane Ball and company is predicting, hey, we're going to have 5 billion, not 1 billion, use in core just by 2025, okay? So you look at that, where is that coming from? Again, it's, I think, coming from this performance curve, okay? You look at the performance trend is not changing. You look at the PUE here, you say, okay, so we've got all the low-hanging fruits, from data center. We're at 1.1, at least best in class, 1.67 average. So we saved all that power. We got all the hanging fruit. We're still on that exponential curve. So that's what's going to happen to your power. It's going to actually increase very, very significantly. So that's where I think some of those predictions are happening. How am I doing, Bapi, on time?
Are you good, Tawfiq? It's just 8:15.
Okay.
You're all good.
Okay, very good. So let's talk about a little bit about that performance, where it's coming from, and the extension of Moore's law. So where is that performance is coming? It's coming from what I'm showing here, we believe, basically that modular architectures. Basically, it's no longer single thread. You have accelerators, you have multifunctions on those CPUs, if you like, or GPUs. And it's all enabled, if you like, with that chiplet technology. And if you look at some really sophisticated, chiplet package today, you see all sorts. You see planar chiplets, you see 3D, like AMD 3D cache, for example, that was presented, I believe, at Hot Chips and other conferences this year. And it's actually allows you to mix and match functions, right? Those chiplets could be very different processes. You could have actually multiple, just like a big die split into multiple compute. You have accelerators, maybe power management, all sorts of things, okay? So we believe that's basically what's going to enable and fueling, that performance curve that I showed you. But it comes with its own challenges, right? And we've seen multiple presentations in this forum about some of those challenges, right? One of them, of course, is test and non-good die. When you have so many chips here, you have this module that's an incredibly expensive one because it has so many of those chiplets. any one of them, that goes bad, then your yield, becomes the cost of yield becomes very, very expensive. So you have to make sure those die are very, very good at the wafer level, and you have very low fallout to assembly, when you do a system like this one. So clearly there's a lot of challenges in test and known good die. Similarly for thermals, right? When you start putting memory on top of compute and IOs and stuff like that,
Hey,
you have
Taufik.
to do, yeah.
So on the test and known good die, um, I've I don't remember where, but I saw that the rise in yields on known good die were really, really high.
I mean,
That
they better be, right? Yeah. Yeah.
so that in practice, it is not as much of a concern as it is in theory. Was the sort of provocative takeaway one somebody made.
It is, I mean, I can't speak to our numbers, but it's certainly getting much better. And overall, clearly, the chiplet world, we believe, is still more economical, even with the testing. But I wouldn't necessarily, underestimate the issues here. You have to, especially as you put new functions and new chiplets, you have to make sure, you have very good tests, very good coverage, at the wafer level. But I mean, certainly, if you look at AMD, we have a lot of chiplet products, right?
Right. Yes. Exactly. So high volume. So somehow somebody's in practice somebody's solving the KGD problem.
Yeah, yeah. Yeah, I don't think it's a showstopper. It's still something, to worry about for sure. Even thermals, right? You have thermal problems. Some of those chips, for example, like you see, vertically stacked, are very, very close to each other, right? So if you have one of those chips in the middle that's very, very hot, then even though some of the other chips may be lower power, they're still gonna get affected by the proximity of this very, very hot die. So that's quite a bit of challenges. And we end up doing these kind of things. But make no mistake, to your point, Bapi, improving yield here by 0.5% could mean a lot. Improving thermals here by a degree could mean quite a bit. So there's quite a bit of challenges. And
Got it.
although you have that product, you're still working to try to get every degree C and every 0.5% of yield. And a lot of innovations still go into these areas, to accomplish that. Power delivery becomes very difficult. You have something like this here, those products approaching 500, maybe 1 kilowatt, and so on, and you have to deliver the power to that. You're delivering. Think about it. Like if you have a 1 kilowatt product and you're delivering that at 0.5 volt, you're delivering 2,000 amperes. Basically to this chip. So it becomes actually very, very challenging, okay, power delivery and power management. I'm not going to talk too much about tests and KGD or thermals, but I'm going to focus a little bit here, actually, on some ideas on power delivery and power management and how to leverage the chiplet world actually to make that more compelling. Okay, so let's talk about here. I think I missed something. Okay. And now maybe it's worth it to look also. I want to make a very quick comparison between the mobile world and data centers, okay? And the mobile devices, laptops are pretty old phenomenon, right? But if you go back 20 years, more than 20 years, maybe 25 years, I actually used to have one of those, even worse than that one, that is heavy, very, very, battery would last barely an hour and a half, basically, and virtually no power management, okay? And you look today, you have all these sleek laptop, well over 10 hours of active use battery life. A lot of those devices, like an iPhone, for example, iPad, or that would last 60 days if it's in off mode, weeks, maybe months of airplane on modern standby. And all of that happens through very sophisticated power management. You look also at their CO2 emissions, basically, and you can see that exponentially, going down, very, very significantly because of that energy efficiency. If you make a little bit more comparison to the data center today, so if you look, you say, okay, you have orders of magnitude of power reduction, but it's a single client. If you have a laptop, you're a single client. If you shut down your laptop, it's pretty simple. You go and shut down everything around it because no one else is using it. You're not affecting anyone, right? In data center, doing something is a little bit harder. If you have a processor and you have 10 customers, doing work on that processor, what you shut down and what you cannot shut down is quite a bit more complicated. There's a blast radius actually because of that multi-client use. If you look at today, the idle mode, the reason why you could last weeks and months on an iPhone or an iPad is because idle power now is extremely small percentage. It used to be in watts, and now it's in barely milliwatts, barely, basically. So leakage is becoming a very small portion of the power, if you like, of the total power on a mobile device. And data center is still considerable, and I say it's kind of, people don't look at it a lot, at my judgment at least. And the reason is pretty simple. First of all, you have no batteries, right? And it's not a customer visible thing. It's not a customer use, that affect user experience. Idle power is very much related to a user experience on a laptop because your battery will drain. Leakage is not, a customer observable, if you like, a phenomenon in data centers. And mobile also, there were things like, even not benchmarks, but Energy Star kind of government, if you like, pushed standards that made the consumer aware of these products. People would pay more money if there is an Energy Star sticker, for example, and people paid for that, right? And there's no such a thing. If you go in today in the data center and rent, for example, or provision a machine, if I want to compare, say an Amazon instance versus an Azure instance versus something on Google, I'm not looking at what energy they're consuming or their impact on environment, quote unquote. It would be very nice if you could have an Energy Star rating on some of those instances, but it does not exist today, right? So the incentive is also not maybe as big. There's still the electric bill, which is significantly, a big incentive, but it's not a visible, if not a user experience visible kind of metric. So now let's talk a little bit, maybe how can use a chiplet world, learn from that mobile experience, and what the kind of things we can do maybe in data centers. Just some ideas, by the way, some ideas. Now let's look at an example. I'm sorry, I couldn't hear.
Hang on, Taufik. It's echo.
Oh. Is it better now?
Yep, works.
Okay, very good. So let's look as an example. For example, let's say you have 100 CPU core. And let's look at the power delivery. Let's say you have a 60-volt voltage regulator down to 1 volt. I think Google does a direct 48 to 1 volt. So that's a real solution in the marketplace today. vCore does that. They have voltage regulators that do that. And let's say you have a single rail here, single VR, single power management system, if you like, feeding 100 cores, okay, on a server motherboard. Now let's say On the right side, I break these into two chiplets. Each one has 50 CPUs. I'm sorry, 50 cores, basically. And now I'm doing the power independent to each one of those chiplets. And let's say I'm going to run those 50 cores at 1 volt. I'm going to go 60 to 1. And here I'm going to go 60 to 0.8. I'm going to run those other 50 cores slower. So it's at 20% less voltage, meaning 20% slower than the top 50 cores, okay? Now, when you reduce voltage by 20%, you reduce power by 50%, at least the dynamic power. Forget leakage for a moment, because it's CV squared F, right? So it's a cubical function of voltage. So now these cores are consuming half the power of these cores. So overall, I would have saved 25% power by breaking this into two chiplets, if you like, each one of 50 cores that are managed independently. Okay, so that seems very simple, right? But it comes with some complications. First of all, now I have two voltage regulators instead of one. So it's higher cost and more real estate, right? Another interesting software problem here you created. Here all the cores are equal. Here some cores are faster than other cores. So now whatever software you have that's going to allocate or provision machines need to be aware of that. So if I have a workload that doesn't require performance, I'm going to send this workload to these cores. If I have a workload that wants more performance, I'm going to send this workload here. So now you created a constraint, right, on the software allocator. The software that allocate and provision machines now has to worry about these cores. They no longer look identical to them, right? So you created some sort of a software allocation complexity, if you like. So I'm going from 1 to 2 chiplets. There's a potential of saving 25%, but there's a complication, potentially more cost to the power delivery. It's not double the cost, by the way, on the power delivery, maybe like 15% extra, but you certainly created more costs here and more complication, but I said 50% of the power. So good? All right, now let me extend that concept and maybe do some more. Now, how do you do that? What kind of voltage regulator? Yeah.
One question. Why do these have to be on the same server motherboard? Why can't they be like two different servers, one running at each running at a different voltage?
That's an excellent question. You're saying instead of breaking here, just do two of those. One has 100, one is just slower CPU than the other CPU.
Yeah.
Which is what's done actually today, right? So hold on that question a little bit. I promise
Okay.
I'll answer. Okay. But that's a very good question, Bobby. That's a very good question. Now, suppose now I have 6 chiplets. I want to do the same thing. And I want to do, multiple voltages here. Now, there are, I believe Intel, for example, is publicly known to use some integrated voltage regulators inside the processor on the same CPU. So that voltage regulator here is actually would be inside the chiplet, inside the CPU. And roughly, because now you're on an advanced process, your voltage regulator on advanced process, you can't have very high input voltage. So let's say roughly around 2 volts, okay? So you can do it that way. It's certainly higher complexity because your voltage regulator now is built on a very advanced process, basically. But it also gives you something really, really nice. Remember when we talked about this 1000 amps or 2000 amps coming into these chiplets? Well, now you're delivering it at 2 volt. So going from 1 volt to 2 volt, it means you half your current. So your power delivery into the package becomes somewhat easier, right? And because they are switching regulator, quite sophisticated switching regulator, they have high efficiency over large dynamic range. So those regulators, reasonably efficient, whether you're outputting 1 volt, 0.8 volt, 0.9 volt, or 0.6 volt, they're quite efficient, right? But they're very complex, very sophisticated. And at least in the publications, I'm not aware other than, Intel already having that in products, right? At least for the publications. Now, there are other ways to do this split with simple LDOs. LDOs are like impedance dividers. They are inefficient, right? Unless your input voltage and output voltage are very, very close. So you're not doing 2 to 1. You're essentially doing 1 to 1, or 1 to 0.8, or 1 to 0.9. So if you're doing 1 to 0.8, you could think of your efficiency as 80%. Just an impedance divider, right? You're going to lose 20% over that impedance divider. So if you do this kind of, power delivery scheme with LDOs, you just have to make sure your input voltage is always very close to your output voltage, right? And if, like here, you become inefficient, right? You become quite inefficient. But if you're only using those here on a very slow core, basically, and you're not using a lot of them, and only on the slow core, you still win. You still win significantly on power, even with the inefficiency of these VRs, with the chiplet version, with the breakout, versus, say, a single monolithic, everything at a single voltage. You can do the math and you can still win very big, okay? Okay, so that's, now I'm gonna get to, Bobby, your question now very, very closely, okay? So now here, I'm saying, with that, you have an opportunity to create potentially chiplets that have different power performance characteristics and run at different voltages. And I'm showing you 6, it could be maybe more than 6, right? And basically, the question that Bobby asked me, well, why don't you just create different CPUs at different performances, right? Which is what we have today. Today, typically in a data center, your visibility doesn't go deeper than the cluster level. You have, let's say, multiple racks in a cluster, and those could be HPC, high performance computing clusters. And if you want a high performance workload, you send it to this cluster. All the CPUs are alike, but they're higher. If you want lower performances, let's say 2.5 volts, you send that to a lower cluster. That's the visibility you have. And typically it creates a lot of hardware, if you like, headache and waste, right? This hardware, for example, here, it's a very different hardware. The power delivery is much beefed up, a lot more beefed up, and generally data centers don't like to have a lot of those, basically, and for various business reasons also. For example, now we have in every region, you have to have all these multiple clusters, very different hardware, big differences in the hardware. So that's a lot of cost. If you didn't have to do that, if you did something like what I'm saying here, whereby at the CPU level, on the same CPU, you could service those machines that are high performance. For example, I could say, hey, A is going to be a low power, low voltage, 2.5 gigahertz. And let's say, B is going to be an HPC, 3.5 gigahertz, and it's going to be very high voltage on the same processor. Then essentially you don't have all these different clusters. Maybe you have only one, right? And that's extremely desirable from a hardware management, hardware cost, all of that for data center. So does that answer you, Bapi?
Yep, more homogeneous.
More homogeneous, yes.
Got it.
But of course, now the software has to see through all of that. They cannot stop at the cluster. He has to know what's in the array, one on the rack, one on the blade, what's on the board, and what's on a given CPU. So now when you provision, if you want to provision a high performance workload, you're going to go deep, in your vision all the way down to the core. And that creates kind of a very difficult software problem, okay? And supply chain management too. What happens if you run out of cores, for example? Now I have to worry about that. I have to think about that too. Now I happen to think all of those problems are solvable, right? But it's actually, instead of a software that essentially it says, oh, I need high performance workload. Okay, let me go to this cluster. Now it has to go and look, oh, I'm going to go here onto this cluster. Okay, let me check which rack. Okay, let me check which blade. Let me check which CPU. Does this board have enough cores anymore? Do I have to different? So it becomes difficult, basically, from the software point of view, okay? But I'm saying, but if you create that infrastructure, I personally believe the software will actually come, okay? So I think that's the fundamental, the fundamental advantage. Because when you break chiplets, by the way, the power generally goes higher because you have all this interconnect between those chiplets. The area goes slightly bigger, again, because of the interconnect, the spacing, and all of that stuff. But overall, I think if you manage that well, you create an opportunity actually to make up, and actually significantly more than make up. Especially if you look at the data center level. Suppose you have that very clever, very smart software that actually uses exactly the exact code for the exact workload. Even if you split into two chiplets, it means I can save 25% of the power. If I have 6, 7 chiplets, I can save well over 50% if I can do that. Because guess what? Most generally of your cores are not, running full speed. Okay. Today, I talked to you about mobile, for example, multi-client versus single client. Look at this situation. Let's say here you have multiple customers and you have one voltage rail. Suppose one customer wants to turbo. They want to run very high for some reason, for a few minutes, right? Because they want to turbo, they're going to take that voltage and raise it. But when you do that, you're going to raise that voltage on every customer, right? Even the folks who are idle are going to see substantial increase of power. I can't say you're idle, shut down, right? Like a laptop, for example, because one customer may be running turbo, but he's affecting the other customer who's not doing anything. So managing that at the data center in the multi-client environment is very difficult. If you have a scheme like this, it's easier, right? Because you potentially could put all those customers turboing on this chiplet. Maybe this chiplet can run low voltage. Maybe I can idle it easier. So it becomes a little bit easier. So the finer grain, the more chiplets you have, if you like. But again, you would need a lot more sophisticated software actually to manage that. So that was basically it. To summarize, I think we all know that Moore's law is slowing down, but performance did not and will not, and it's going to continue on that trend, right? So many people have argued that this heterogeneous integration basically is what's helping that performance scaling, obviously, because of the different functions you can put in on the same package. And the chiplet technology is certainly inherently better suited for that fine-grained power delivery and management, like I showed you. But with the fine-grained hardware, you also need that fine-grained software actually to reduce overall data center power significantly. And that's it, folks.
Hey, Taufik, that was really, really great presentation. Can you just go back to your last slide? I just want to make sure I understood. The one before this summary slide.
This one?
Yeah. So what you're saying is that when you say fine-grained software, say the request comes in for high powers or HPC applications where they want to run at 1.1 volts, then what you're saying is you would pick, the software would be smart enough to pick all the B chiplets.
Yeah. Yes.
I see.
All the B cores.
And today that is not the case. That's not how it works. Is that
No.
what the model for the future, specifically AMD and?
I can't speak anything honestly about our roadmap and what we think and
Okay.
specifically, but today, to my knowledge, generally, if you now go and try to buy on the, uh, basically it's all, cluster based. Basically, you don't have that visibility of the software. Here, the core, somehow each core on that CPU have to tell that software, its power performance capabilities, and you see what I mean? So yeah, it's a lot more sophisticated.
Okay, thank you.
I
Understood. Thank you.
honestly think actually, as hard as the hardware problem is, the software problem is even harder. Actually, it's not that simple, but yeah.
Hey, Tawfiq, I have a question. So, are you aware of any advantage that the co-packaged optics is bringing to data center to reduce power consumption?
From a power consumption point of view,
Yep.
yeah, I'm not very much into that, to be honest with you. I know there are several people looking at this, but I'm not into the, package optics side of things. You mean inside the package, right?
Yes.
Yeah. No, I'm not aware of that. I mean, I've read some papers, honestly, in the industry that says generally optics would help you a lot if you have distances of the order of a meter or so, right?
Mhm.
At least some papers. If you're inside the package, I do not know, but I know people are looking at that stuff. I do not know.
Thank you.
Sure.
So the
Other
basic
questions?
the basic thesis is when load is low, switch to a more power efficient core, and when the load is high, bring in your juicier core up for sort of the data center version of the big little that the mobile guys use.
Yeah. It helps you, it helps you, think of it as if I look at a laptop, there's a single client. If I have, let's say, 100 cores and I break them, let's say, into 5 chiplets, and now it's not single client, but maybe I can actually achieve close to the same thing because I can distribute those clients more effectively along the different cores without, like you said, without having to have multiple clusters. Okay, I can do it with a single, essentially, piece of hardware.
So heterogeneity within the chip for homogeneity in the data center.
Yeah.
Okay. Any
Hello.
other questions?
Even, by the way,
Yeah.
even with the cluster distribution today, if like if I have a chiplet, even if I have multiple cluster, within a cluster, I have much better chance on managing those and shutting down versus basically if I have a single monolithic, a chip.
Got it. Shalab has a question somewhere.
Yeah. Hi. So, my question was, do you also know like what is the percentage of power consumed in data center interconnects in the data centers, and do they also get similarly like switched on off or like reduced speed, increased speed in the interconnects?
You mean, do you mean like chiplet to chiplet interconnect, or you're talking about like rack to rack, all the interconnects in
Rack,
data centers?
yeah, rack to rack kind of interconnects.
Yeah, no, I don't have a number for the split, say between server board, and the interconnect. I don't have that chart, but I know there is also power management, at the data center level, that looks at total power, for example, at the rack level, and manages, I think Microsoft have some published paper about that called power capping. So they do pretty good, power management at the rack level, not just at the CPU level. But in terms of breakdown between the server boards and the interconnect, I do not know the power breakdown now.
Okay. Okay.
I
Thanks.
would
But
imagine,
do they also?
I would imagine it would have to be small, relative, of course, to the server boards, right, which consume most. I mean, I'm pretty sure most, the vast majority of power is consumed, on the server board versus, versus the interconnects.
Okay. Yeah. Thanks.
Yeah, I don't know the allocation. If I look at the server rack, for example, and say, okay, I know the server board, and I know how many boards I have to fit in a server rack. I don't know how much that interconnect actually consume, or even figure into the equation of the total rack power. But I'm pretty sure, Shalab, it's a small portion of the total rack power.
I believe it is more for the switches, right? For the top of the rack switches, etc.
Yeah, the switches consume, definitely, yes.
And do you know if the interconnects are also like reduced power or increased power based on the traffic or data transfer rates? Do they switch with the speed?
I don't have the breakdown. I would imagine the case, yes, but
Okay.
I don't have the numbers.
Okay, thanks.
Sure.
On all these general questions, do you think it's worthwhile trying to begin to draw the entire system architecture from a power perspective so that people can instantly see where the power is being consumed? Because we say the switches are like with general purpose data centers, you're always going up and down these 2 or 3 layers of switches, which is a huge amount of power. And then we're trying to get CXL up to memory bandwidth. So we're talking about terabytes per second going up and down the network, and the power just gets completely out of hand. But nobody has an easy way of visualizing it. So I've been trying to push for, could we draw architectural block diagrams and show the energy or the power, so people can go, oh my God, I'm focusing too much on optimizing the power of my core, and I should be just a simple upgrade, a simple assessment of how do I wire my network up for my particular application.
I mean, it's definitely very useful. I know, I've seen papers. I haven't worked in the field, but a lot of the power, like you point out, and I think Shalab, is actually consumed in moving data versus actually processing data.
Right.
And I think it's definitely useful. I haven't, I've not seen it. I've seen papers, but I think it's definitely very, very useful.
You can imagine a very simple software tool to visualize it. Like a bit like the power analyzers, the static power analyzers on PCB, dynamic ones. Go beyond the PCB, go to the entire computer data center.
Yeah. I think somebody like, Azure, I'm pretty sure, or those guys maybe can do that.
They may already have their own proprietary software stacks for power analysis, but it would be good to make an open public one.
Yeah.
All right. Taufik, that was really engaging. Thank you.
Thank you. Sure.
Any other questions for Taufik before we end? Thanks, Taufik. That was really nice. Thank you.
Thank you. Thanks, folks.
Have a good weekend, everyone.
Bye-bye.
Thank you. Thanks, Tawfiq.